So for right now, we all know sine of theta, cosine theta, tangent of theta. Sine is what trig function over what trig function? Or for a right triangle trig, what is sine? Alright. So this is all based off of your right triangle. Remember, when you have your right triangle, theta can go of either two angles, and then the opposites and the adjacents are all based upon where theta is placed. The one thing that never changes is your hypotenuse. Cosine.
Adjacent over hypotenuse.
And last but not least, tangent. Okay. From there, we also we introduced what are called the inverse trig functions, which basically is the reciprocal of the standard. We have cosecant, secant, and cotangent. Cosecant is the inverse of sine, so it becomes hypotenuse over opposite. Hypotenuse over the adjacent, and adjacent over the opposite. Those get you your inverses. And this is stuff that we worked on back in 13.1. We've seen this before. Now, what's going to happen today is that we're going to take this and place our right triangle upon the, on the unit circle. But not going to call it the circle right away. We're just going to call it on a grid. All right? So let's try this. Bless you. Let's say we have a grid, and I have an ordered pair. My ordered pair is 3, 4. And I'm going to plot that in my grid. What quadrant does it go into? It goes in the first quadrant. Go over 3 and up 4. And there's my ordered pair. Everybody agree? All right. Now, this horizontal distance is 3. My vertical distance is 4. Which means I created a right angle there, correct? What's the hypotenuse? 5. Everybody okay with that? All right. So now, at this ordered pair, I have an x value of 3. I have a y value of 4. What happens now is what we're going to call is theta. Theta of the angle that's created by this ordered pair is here. Notice how theta is placed, where a vertex is at the origin. Everybody see that? So what I want to do now is I'm going to write the trig functions of theta with the xy coordinates of 3 and 4. We're going to do the same basic idea. Sine is going to be opposite over hypotenuse. Everybody agree? What's the opposite in this case in relation to theta? 4, what's the hypotenuse? So it's 4 over 5. All right. Cosine is adjacent over the hypotenuse. What is it in this case? Good. And tangent. 4 over 3. Now, I will say one thing. I apologize. A lot of times when I'm writing out trig functions, if I'm talking about sine of theta or something along those lines, I tend to forget to put theta in a lot of times. It really is there. I just always seem to forget to put that angle in here because that's what we're talking about. All right. So if I forget, there's probably supposed to be something there. What's that?
Oh, that's a really good way to write theta. I'd
I
always
was
draw the
just thinking
circle
that.
and draw the slash, but then you can just
Yeah.
go right
I was
into
about to
it.
say.
Oh, you guys never did that? I
No.
never showed. Yeah, you just kind of make it a little bit, make it
Yeah.
a little bit more of an oval circle.
You see, I was like, that's a good way to write it.
Yeah.
And he said it, and that was crazy.
It's like my Jay Leno faces. Remember the Jay Leno faces?
Yeah.
Yeah, the brackets.
Yeah.
That one wasn't good.
Yeah, I'm a little out of practice. A little out of practice. All right.
Brackets are.
Now, should I walk through the inverses of these, or we can all kind of do inverses, right?
Oh, yeah.
All right. Let's take a look now. Look at the ordered pairs. It's the x and the y's. Everybody see that? This is y, this is x, this is y over x. Which basically is starting to tell us then, when we have an ordered pair, the sine of a theta is going to be y over r. And r is playing the role of the hypotenuse here. If I drew this going all the way around, sorry. If I drew that going all the way around, wouldn't this radius stay the same all the way throughout the circle? It should stay the same all the way around. Now, in order for us to figure out that value of r, which we did real quick, you did it was 3, 4, 5, what proves that it's a 5? Pythagorean theorem. So what happens here, let me move a little of this messiness out of the way here.
That's so cool.
So much I
Yeah.
I'll tell you, I can't even imagine not having this board anymore. Ready on
That's so like 4 years ago, right?
So
Yeah.
What are
This
chalkboards?
value of chalkboard, this value of r is always found by using Pythagorean theorem. It's the hypotenuse, but we're going to use it. We're going to use the letter r for that because it's also going to be playing the role of the radius of the circle. We will a little bit, yeah. So here's what we can do, guys. We can take these trig functions and we can rewrite them in terms of x's and y's from ordered pairs. So I now can say that the sine of theta is going to be y over r. The cosine of theta is x over r. Thank you. The tangent of theta is y over x. And you can get all these things just from the ordered pairs. The inverses. Well, you just flip the fractions. The inverses, the cosecant is going to be what over what? R over y. The secant would be x. Oops, sorry. It would be r over x. And tangent would be x over or y. Did I say tangent and cotangent? Excuse me. So what's nice about this now is that we're going to be able to take any ordered pair, place it on a grid, visualize where theta is coming around, and we're going to be able to write out all 6 trig functions given an ordered pair. Yes, sir?
What is like the circle? Because you're getting r equals the square root of x squared plus y squared.
That's just Pythagorean theorem. I'm just saying Pythagorean theorem. It's just the r.
5,
Yeah.
the radius line?
Yeah. What's 3 squared plus 4 squared?
I know, but I didn't know like where the circle was, if it was like on the 30 or something.
Oh, I see what you're saying. The circle in quotation marks here is basically the center is going to be placed upon the origin. And that r value is going to rotate it around the axis. And that's going to allow us to find all these different ordered
So
pairs.
the point is on the circumference of the circle.
Yes. Yeah, it's on the circle.
Oh.
Okay, does that make sense? All right. Let's look at another example then. Just did that one. Negative 12 and negative 15 are my ordered pairs. And I want to visually represent where this is and then write out all the trig functions that has that ordered pair, or of theta. Well, what quadrant will this lie in? The third quadrant, so here's my ordered pair. What's my radius?
question.
I get the square root of 369. Do you know how to simplify radicals with your yellow calculator?
Yeah.
Yeah.
How do we do that again?
369 divided by
Good. Go back to go to your y equals. Type in 369 divided by x squared. Go to your table. In the table itself, you're looking for a positive integer value, or excuse me, the smallest possible positive integer value as you're scrolling through. 1, 369, 3, 41, and if you keep going down through here, there's nothing else. You'll just get to repeating decimals after you get down around 1. So that means that your answer, to simplify that, would be 3 root 41. That's the value of r. Everybody okay with that? Simplified square root of 369. So this is r. Now, what you're visualizing and what you're building here is this right triangle that's formed with side lengths of 15 and 12, but they're negative because they're in that third quadrant. Okay. Let's see, this went backwards. This way was 12. Sorry, I just realized that too. Now, you created a right triangle. All we have to do now is write out our trig functions. So r is 3 root 41, x is negative 12, y is negative 15. So that means the sine of theta, given that information, now theta is going to be formed here. The sine of that is negative 15 over 3 root 41. Is that a happy looking answer? Why not? It's got a square root in the bottom here. So there's and what's nice then is you can actually simplify this rather quickly. What can I do with the negative 15 and the 3? So this is negative 5 over root 41. Are we okay with that?
Yeah.
Let me move this over just a little.
You're so funny, Derek. Ew, that's disgusting.
So when I do that,
Don't do it again.
please. When I go to rationalize my denominator, can everybody just look at that and tell me what it is without having to do any work? What is it? Good. So this would equal negative 5 root 41 over 41. And that's the sine of theta. The cosine. X over r. Negative 12 over 3 root 41. So you get negative 4 over root 41. And so on. Take a second, write out the tangent, and then write out your inverses. And we'll see what you come up with.
Should we radical?
You rationalize? Yeah, absolutely. You always rationalize your answers here. You're going to always rationalize. So take a second.
Not up like a thing and then.
So as you continue on,
Wherever you want.
tangent theta was y over x, which was negative 15 over negative 12. All right? Those are your three normal trig functions. Your inverse trig functions don't take very long to go through once you get these, because your inverse, all you have to do is flip them here.
Do it.
Flip them before you're rationalizing. So my cosecant would be root 41 over negative 5. I don't have to re-rationalize it. If I did that with my negative 5 root 41 over 41, and I flipped that, I'd have to do a lot of rationalizing. It'd be a big pain in the butt, and nobody would enjoy doing that at all. So, take what's easier to work with. Same thing here with the secant. It was negative root 41 over 4. Does it matter who gets the negative, the numerator or denominator? Doesn't matter. And then the last one, the cotangent, you get 4/5. Is everybody okay with that? All right. Get all 6 functions off of that, please.
All right.
All 6.
Yeah, just sing that.
Right away.
What quadrant is this in?
Second.
Okay.
Secant.
Four. Secant phase.
Oh, no.
What kind of triangle is that?
It's 45, 49.
It's a 45, 45, 90, isn't it?
Yeah.
So 45, 45, 90 placed in the second quadrant. So your theta's here. Your radius is the square root of 2. So here's x, y, and we know r is root 2. So the sine, 1 over root 2, otherwise known as root 2 over 2. Cosine, negative 1 over root 2, otherwise known as tangent. Well, it's 1 over negative 1, so it's negative 1. The inverses. Again, by going to do the inverse, it's just root 2. Secant, negative root 2.
Mr. Murphy, I still don't understand why secant is cosine, but cosine is sine.
And talk to the Greeks. I don't know.
Cosecant.
Yeah, that's what I said.
I know. It's become of this discussion every single year we get to trigonometry. Why
Hey,
isn't
that's
that?
what the kids about 1,000 years.
Yeah.
For real.
It's up real good.
That's kind of what they were doing. So,
Let's get paid.
all right. What's that?
Oh, no.
Hold on, guys. Hold on. What's that?
Somehow got the negative and
Oh, you probably
you always do X.
X goes to cosine, Y will go to
I mean, like when you're writing, you could also like flip it like Y. Yeah. Like if you drew it like go up and then across and then that's what you would.
No, because remember your ordered pair. But even if you drew it the other way,
So you start with X.
because if you go over this, if you go up and over, you're still going over negative 1. You went up 1.
Yeah, but then you have like the.
Oh, I see what you're
sign
saying.
would have opposite. Yeah, opposite.
But that's why we always go left and right first, and then up and down.
Okay, so X. Okay. Alright.
Now, this is what's getting us to be able to do, guys. These, obviously you figured out, this is a special right triangle. And we've dealt with this before as 1, 1, and root 2. Now, last week, we started talking a little bit about that,
That's all right.
about your unit circle. And we already found that the cosine and the sine at 45 degrees was root 2 over 2,
Yeah.
root 2 over 2. All right. We also worked around, we also walked around the unit circle from this spot.
Typically.
Jesus.
That was,
Are you still
that was
going
not
at
me,
it?
Dave.
Guys,
Mr. Murphy. that
there's
was-
a fan on, it's gonna blow towards me at some point, so let's just cork it.
Not me. And the one's going to mics.
Like I said, as we went through this last week, the ordered pairs here were root 2 over 2, root 2 over 2. If you look at your unit circle that you've already created, these four angles all have the root 2's over 2. Oops. Now what I want you to notice is what happens to the signs, like SIGN. They're both positive here in the first quadrant. What's negative in the second quadrant, X or Y?
X.
So that means cosine is negative in the second quadrant. What's negative in the third quadrant? So that means cosine and sine are both negative in the third quadrant. What's negative in the fourth quadrant?
Y.
So sine is negative. The reason this happens, if I'm drawing a cross here, horizontal lines share what in common? The same what value?
Y.
The same y value. Notice how the y values are the same for that ordered pair. What do vertical lines share the same?
X.
They share the same x coordinates, therefore these two guys are the same x. They have the same cosine. Back down over here, the y values are shared again. The x values are shared here. What's going to happen eventually, or not so much today, but more so tomorrow, when we break into the 30, 60, 90 as well, is that by using the properties of rectangles and squares and parallel lines and perpendicular lines, you're going to be able to develop all of your angle measurements for your special right triangles via the unit circle this way. By using the sine value is y over r, cosine value is going to be x over r, tangent is going to be y over x. You're going to be able to calculate these things without using your calculator, because you won't have your calculator when you do these parts on tests. So you guys know, all right? Questions so far? All right, let's talk a little bit about something that's called a quadrantal.
Oh,
Special name.
Quadrant.
Special name.
We discussed, I think I might have made mention of it last week. A quadrantal is an angle that lies on an axis, basically what we're looking at. And your quadrantals are 0, 90, 180, and 270. It's just if you're on the axis, that's a quadrantal. Now, what I want to do here is kind of help develop what it means to get your trig functions at your quadrantals. But in order to do that, we've got to kind of draw something. When I'm at 0, what's my ordered pair here? I'm sorry, at 0 degrees. Let me change this up. 0 degrees, 90 degrees, 180 degrees, 270. What's my ordered pair there? Something 0. Good. Yes, sir.
Oh wait, I was gonna do the order. Wait, what are we doing?
Is it infinity?
Well, it's not infinity. What is this distance going to be called?
Radius.
X.
X.
Okay.
X up?
What's my ordered pair up there?
0.
0 and y. Good. What is it here? What is it? Negative x and, okay, and then down here? 0, negative y. Okay. Now, here's what I got to figure out is how am I going to get my value for r? What was the formula for solving for r again?
X squared plus 1 squared.
Yeah. Exactly. So if I use this, my first ordered pair here, I get r is going to equal the square root of x squared plus y squared. So what is my r value here?
X plus 1.
What's the square root? Well, hold on. What's y?
Yeah.
Okay. What's 0 squared? What's 0 plus x squared? What's the square root of x squared?
X.
Okay, so what's r? X. Yeah. What's r here?
Y.
What's r here?
No,
Ooh,
just X.
it's just x again.
Square.
It's just x again here. Everybody see that? Because when you square that, it becomes positive. And then what's my r value here?
Y.
Okay. So what this is allowing us to be able to do then is still reuse all of our 6 trig functions on our quadrantals by using that x, y, and r. Same idea. Take a look. If I want to find the sine, I'll split this out here if the button wants to work. If I want to say the sine at 90 degrees, I'm up at 90 degrees, that means that it's going to equal y over r. Well, what does y equal in that case? Okay. But if you look at it here, isn't r y? I'm just going to leave it. In my ordered pair, what is y? Y, right?
Yeah, y is y.
And what is r?
Y.
Okay, what's y divided by y?
Oh, wait, so well, either way it's,
You were on the right track. I just was trying to keep it in
I
terms.
understand.
Okay. So that means the sine of 90 degrees. The sine of pi over 2 is 1. Okay. Cosine. It's going to be x over r, which in this case is 0 over y, which is 0. That means that the cosine of pi over 2, cosine of 90 degrees, is going to be 0. The tangent of 90 is y over x. Well, y is y, x is?
0, no solution.
Now, we don't say no solution, though. We say it's
Undefined.
undefined. So this is y over 0, so it's undefined. So the tangent of 90 degrees would be undefined. Now, to do the inverses, all we do is flip the fractions.
1 undefined.
What is the
0.
inverse of 1? 1.
What's the inverse of undefined?
Well, what's the inverse of 0?
0.
Well, remember, this is 0 over 1. I'll just put it over 1 for right now. If I flip that, it becomes 1 over 0, right? So it becomes undefined. Now, what about the cotangent then? It becomes 0. Think about when you did slopes. What was perpendicular to horizontal lines? Vertical lines. And what was perpendicular to vertical lines? So if a perpendicular line had a slope, or excuse me, a horizontal line has a slope of 0. A perpendicular line has an undefined slope. It's the same basic idea. They're inverses of one another. They're reciprocals. Okay? So all we have to be able to do here is write out what they are for sine, cosine, and tangent on the quadrantal and just flip them. The inverse of 0 is undefined. The inverse of undefined is 0. The inverse of 1 is 1. That's kind of easy. All right? Now, again, this is getting us to be able to, when we're getting closer and closer to be able to work with these things, this value of r, because it's on the x-axis, is still going to be the same value of r here, still going to be the same value of r here. Oops. Because the radius of this circle will not change. Going all the way around, that radius of the circle isn't going to change as we go through it. That's why when we work with quadrantals, to help us show where the sines and cosines and tangents are changing values. Okay? Does that so bad? All right. So let's do this. Get me the 6 trig functions at 180 degrees, please. The 6 trig functions. So far, so good?
Yep.
All right. Yes, sir.
First sine, is that 0 over x?
Yeah. 0 over negative x.
0 over
And what's 0 divided by anything?
Right, right, it is.
Yeah, that's all. Yeah.
Um,
Oh, sorry, sorry.
No, it's fine, go ahead,
No, no, go ahead, finish. Go ahead, finish on those.
I'm still trying to find out.
Oh, okay. Yes, Jake.
So 17 or 0, why is it 0?
What is that?
Okay, now like sine and tan
Yep.
are 0.
Remember.
Get y cosine 1. But
All right, sine is 0. Oh, okay. Why is this negative 1?
yeah, that's
Oh.
because x is negative, right?
Yeah, it's x over r. So x in this case is negative x. R is x, so it's negative.
Right.
1.
That's what I'm talking about.
Yeah.
And
The other two are 0 because it's y over r. Well, y is 0 and r is x. 0 divided by x is 0. And then it's the same thing here. Okay? These are your quadrantals. Go ahead, Willis.
So when it says like theta of the angle, it's referring to like this, right? These sort of here where r equals x and it's negative x and 0. That's what we're using to.
Yeah, in this case here, this is what you're finding it on the quadrantal,
Right.
which
Okay.
at 180 degrees, that's playing the role where theta is going to wind up at, okay? Now, what I want you guys to do tonight is just a few of these to start out with. It's on page, I think I had it open, yeah. What is this, 788, 26 through 36. 788, 26 through 36. So on page 788. What you guys are going to be doing is you're going to be working on the you're going to be working with the quadrantals and you're going to be working with some ordered pairs. And all you're doing is finding the 6 trig functions on all those. Working on some rationalizing and simplifying of some fractions. Do your best not to use a calculator, ladies and gentlemen. Do your best not to use a calculator. You might even notice that I've done 2 or 3 of these already to start with.
Yeah, there's 2 or 10.
Okay?
So